This learning sequence is about Faraday's law of induction. And you may recall earlier in the class, I told you that Faraday was the greatest scientist that's ever lived. I stand by that. And let me tell you a little bit about why. Faraday was not born wealthy like most scientists. He was born sort of working class. His destiny was to just take elementary school and then be apprenticed to a bookbinder and to make books. And there's nothing wrong with that. But he got very interested in science from lectures by the Royal Society, the public lectures they would give. And he'd get excited and read about it and think about it and have his own ideas and do experiments and show them to the scientists at the Royal Society and say, hey, I want to get involved. And they kind of said, yeah, whatever, go away. And he bugged them, and eventually they let him be the janitor. So he was the janitor of the Royal Society. But once he had his foot in the door, that's all he really needed because he was such a brilliant experimentalist. But what's interesting about Faraday is he didn't really know much math. He could add and subtract and multiply and divide and maybe a little algebra, but he certainly didn't know any calculus. But despite not knowing any math, he basically invented field theory. He could always think of the right experiment to do to figure out what's going on, and he visualized fields. He called them the lines of force. So surely we can understand fields if Faraday understood fields, because he didn't even know much math. So he was very big in the early days of figuring out electricity and magnetism, and then he got off in consulting. And as soon as Faraday goes off and starts doing consulting to make a lot of money, everything goes crazy. So let's look at the 1820s. What's going on in the 1820s? Well, they knew that you could get from electricity to magnetism. This is what Ørsted showed. We did the demo ourselves. If you have a wire with some current, it makes the magnet move. So we know we can make magnetic fields with current. But that's really not what you want. Well, you want that, that's fine. But what you really want is the other way, because currently at this time, the main sources of electricity are triboelectricity, so rubbing cats, Wimshurst machines, things like that, and batteries. And batteries are kind of big and messy. These lead acid batteries they had then that we still use today are not real convenient. So it would be nice if there were some way to go the other way. Can we go from magnetism and get electricity? It would seem like we should be able to because they seem related. So a lot of experimentalists were setting up things kind of like this. Here's a bunch of loops. We know magnetism likes loops. Here's a bunch of loops of wire going to something that real sensitively measures currents and voltages and electricity. And they just wanted to say, is there anything I can do with this magnet to generate electricity? So they'd say, well, let's put the magnet inside the coil. And let's check. No, nothing. And then say, okay, well, maybe if we put the other end inside and see if we get anything. And no, again, nothing. Maybe if we put it in here, we'll see something. So then we have check, no, nothing. Nobody could figure out if there was a link between electricity and magnetism. So what if we just set it on the outside and then the field kind of goes in? We have a look. No. Can't do it. Nobody could figure it out. Well, then after a while, Faraday had had enough consulting, wanted to get back into research and wanted to work on a problem. And he said, I'm going to find this link between magnetism and electricity. And everybody said, no, we tried that for 10 years, don't bother. He said, no, I'm going to figure it out. So he goes on vacation and starts doing his own windings, making his own instruments. So he was really good at experiments, making instruments. He had the most sensitive galvanometer of anyone around. Winds all these coils up. He doesn't set up this exact experiment. It's something of a different experiment he did. But basically, he did this. And there it is. You got to look when you're making the change. Faraday's law of induction depends on a change in the magnetic field, not just having a magnetic field near the coils. So because he looked at the right time, but really more because his instrument was one of the only ones sensitive enough to really see the deflection, he was the one that found the link between getting from magnetism to electricity. It has to do with being able to have a magnetic field change inside of a coil. So let's look at Faraday's law of induction. So what Faraday discovered is now called Faraday's law. It is the fourth of the Maxwell's equations that we are making our way through. We may need to modify one a little bit, but at this point we will have them all. So if we want to put it in sort of plain language, a changing magnetic flux through a wire loop induces an electromotive force in the loop according to we'll just give the equation is that E, a curly E, equals negative d phi b dt. So let's talk about what these things are. So there's the law and the equation, and now let's look over on this side. What is this E? This E stands for, I wrote it up there, electromotive force. It's kind of an old-fashioned word. It basically means, if I had to even define it, we'll define everything, it's the result of something moving charge. It's also called sometimes just EMF for electromotive force, little e, little m, little f. So it really just means anything that causes current to flow. So sometimes you'll have a battery and it gives you a delta V, it gives you a voltage, right? A 9-volt battery gives you a voltage. Sometimes that's called the EMF. The chemical reaction, the battery does work to move charge carriers across a potential difference. It's doing work. It's creating an electromotive force pushing the charge carriers. So that term has survived to this day. Eventually we'll be getting rid of the E in this equation. But for now, we'll just think of it as what it is that made the current flow. When we did the demo, you saw the needle shifted. Well, that was measuring the current in all the wire loops. So if we have our loop that looks kind of like that, and we have our B field going through it like this, and that B field is changing in time, then we get a current flowing. And the EMF is what makes that current flow. So EMF is in volts. It's not a current, it's a voltage. But if you want to relate the EMF you induce, the voltage you induce, to the current that flows, then it looks just like Ohm's law. You say the EMF equals the current times the resistance of the loop. Okay? So EMF is like a voltage in a loop. But it's a little different because it's hard to imagine a voltage in a loop. Right? If we have a circuit, then you put a voltage, you have 2 points, and you break the circuit, and you apply a voltage with a battery. But here a voltage is just building up, and a current is flowing. Well, where's the voltage? Where do you apply it? It's hard to think about. If you put it here and here, the current would flow down the side of the loop. One way to think of it is it's like you broke the loop, and you applied a voltage with a battery like that. Okay? But that's why we just call it an EMF. All right, the right-hand side is something we've seen before. Phi B is the magnetic vector flux through, in this case, through the loop. So we define this vector flux just like the electric vector flux. It's the B field dotted with the area vector. Or if you want to do an integral, it'd be the integral of B dot dA. But we have to take this loop, give it an area vector. We'll be doing this more later. And then we can define these two things. So if your magnetic vector flux changes in time, that induces the little electrical effect that we saw. And that's really what Faraday discovered. You can't just put a magnet near a bunch of loops. You have to have the magnet move. You have to have the magnetic field change. So Faraday's law applies to any situation with a changing B field. So let's just draw a bunch of cases. It'll be good practice to kind of give us a feel for Faraday's law. So first I'll just draw a current loop here, or a loop of wire, and we'll say, okay, it has to have an area vector. We have to decide which way is positive, basically. And then behind it, I'll draw a bar magnet like this. like that, where this is the North Pole and this is the South Pole. And this is similar to the demo we did. We were pushing a magnet through a bunch of coils. Let's see. So we know that the magnetic field comes out like that, and like that, and like that. So it wants to go from north to south. So in this case, the magnetic field is coming out of the loop in the same direction as the area. And let's imagine that the magnet is moving that way. So we have the North Pole moving towards a loop. Let's think about what Faraday's law tells us will happen. Well, we have a case where the flux is changing because the strength of the magnetic field is large right near the pole and it gets weaker as you go away. So if you move a bar magnet like this near a coil or near a loop, it will change. So let's look then and think about it. d phi b dt is what here? Here it's positive. So you got to think about the rate of change of the flux. So if we have this loop getting closer to the magnetic field intensity is bigger here than it is here. So if we move towards the bigger part, then the b dot dA here is weak, and as this gets closer, it'll get bigger. So d phi b dt is positive. So according to Faraday's law, the EMF is negative. Well, what does that tell us about the direction of the current? Well, we have to decide what is the direction of positive current. We decided that when we chose the area vector. Okay? We made the area of the loop positive this way. So if you apply the right-hand rule, you say, okay, positive current is this way, from the front of the loop going towards the back of the loop. But the EMF says it goes the other way. So the current in that case would go from the back to the front. So that's pretty much what would happen. But now we can compare different kinds of cases. What if we had the same thing, loop, area vector, magnet, like that, but now we have the South Pole here and the North Pole here, but we still haven't moved towards the loop? Well, now the field lines will look kind of the same, kind of like that, and kind of like that, except now they're pointing in, right? The field goes from south to north. But we have the area vector going the same way. So now the flux is negative. Okay, so d phi, the flux itself, the value of the flux is negative. But as we move this closer, you get a more and more negative value. Right? The flux is going down. So the rate of change of the flux is negative. Not only is the value of the flux negative, but it's getting larger and larger negative magnitude. That means its rate is also going negative. So when you just do these problems thinking about them, you have to keep up with what is the magnitude of the flux and what is the rate of change of that magnitude of the flux. It's tricky. So anyway, if that's negative, then according to Faraday's law, there's a negative sign, so the EMF is positive. If the EMF is positive, then the current will go in the positive direction, defined by the area as that way, from front to back, like that. We'll go around. Okay. Let's do one more, just to seal it here. Let's see. There's a loop. Again, we're putting the area this way. This is the front. That's the back. And we have bar magnet north-south. We'll go back to our original bar magnet, but we'll make it go that way. Now let's pull the magnet out. All right, so the field lines go like that, and this field line goes like that. Okay, they go out because we're at the North Pole. So now we're pulling it away. It's going from some high flux, a lot of field lines going through, and when you pull away, less field lines will go through. On all these, the way I'm drawing it, it looks like you're going to retain 4 field lines. Keep in mind, these are not technically perfect field drawings. So understand that here the field intensity is high, here it's lower. So we're pulling away. So when we pull away, we have, let's see, here we have a positive flux, but it's going from high to low as you go down. So d phi b dt is negative. The flux is decreasing when you pull that thing out. If d phi b dt is negative, then the EMF that's induced is positive. Area is that way, it's this way. Same as this condition. So you can see the EMF you get, it depends on many things. It depends on which way the B field is, whether the B field is going up or down, north, south, south, north. All these things can flip it back and forth. This is not the only way to induce an EMF. We can draw many other interesting situations. We could have a current loop here. So let's put this thing, send some current into here and out here. And let's make that current vary in time, some time varying current. And then we could put our loop, our other loop, nearby. Okay? So we know what this thing's going to do. This loop is going to make a B field. Let's see if the current goes around like this. Then it's going to have a B field pointing out like that, like that, and it's going to go like that. So this current loop that's having current driven in it at some time varying rate will generate a B field inside of this loop. And let's see, the way I've drawn it, let's say that di dt is positive. So let's say the current is increasing at some moment in time. Then this B field is positive. B field is increasing. Let's define this area as out. Let's say the area goes that way. So you can't see it coming to that surface right there. And these are all B lines out here. If that's the case, then if b dt is positive and it's the same direction as the area, then d phi b dt is positive, so the EMF is negative. Let's see, so if the EMF is negative, then this is the way around that gives you the positive A, so the current will go that way. So the current induced is the opposite direction as the current that did the inducing. So we'll see more things like that later. There's lots of ways to do this. Let's have a current going along a wire. Let's see, right-hand rule, the current's that way. It's coming out of the board here, big field here, and then it gets weaker as it goes away. So remember, it circles around. And it gets weaker. There we go. What if we just have a current, a wire loop and just let it fall due to gravity? Or just say let it move down. Well, it's got a changing magnetic flux through the loop. It's going to experience an EMF. It's going to have an EMF induced in it. We can think about, without writing it out, the direction. Let's see. If we define the area vector out this way, so that way is positive, the B field is going in against the area vector, so the flux is negative, but it's getting smaller. It's negative and getting smaller, so d phi b dt is increasing. It can be negative, but increase. Positive EMF, therefore, is negative, and if the EMF is negative, then that's the positive direction the current goes that way. Okay. You can always get there. I know you want to see one more, because I got to fill the board. Here is a piece of iron that, as we talked about, is a ferromagnet. So if we take a coil and wrap it around this iron and send a current as a function of time through that coil, it will align the magnetic domains in the iron. It actually will do it all along the iron. So often ferromagnets are used to sort of control a magnetic field in space. If we put another coil, it looks just the same here. We could ask ourselves, what kind of a current is induced? Well, let's see. So here, this current is going around the back, and in the front, it's actually making a field this way if the current is positive. And so let's see if di dt is positive. If it's increasing, then that means the magnetic field dB dt is increasing, is positive if it's going that way. And let's see, if we assign A positive this way for each one of these loops, positive to the right, then d phi b dt is, let's see, so B is this way, d phi b dt is negative, and it's increasing, so the change is negative, so the EMF is positive. And let's see, if the current goes around this way, that's a positive direction. So the current comes around this way. And sure enough, it goes in the opposite direction, just like it should. Okay. So the point of all this is it's not just a permanent magnet going through a loop. You can do all kinds of different setups. Anytime you have the magnetic flux changing in a loop, you'll get an EMF. The induction that you get depends on geometry. So by that, well, there's two things I mean by that. So one, EMF equals minus d phi b dt. Let's think about what phi b is again. That's the magnetic vector flux. So really we mean minus d dt of the integral of b dot dA. That'll catch all the geometric variation if the B field is changing inside the loop or whatever it might be. So what that means though is there's a dot product here. So I think I misspoke in the last board. I said that anytime you have a B field in a metal loop, you'll get induced current. Well, no, actually, this needs to not be zero. Okay? So what I mean is, say we have a magnetic field pointing this way. It's changing in time. If we have a nice little loop, wire loop like that, with its area vector like that, B and A are parallel, B dot dA is just B times dA, you'll get a big induction, assuming the magnetic field is changing. But if you have the wire loop in the plane of the board with the A vector sticking out, then of course B dot dA will be zero. So that's the one way you can avoid induction, is to not have the loop lined up where you actually get any flux. Also, another geometric parameter sort of, also for multiple loops, the EMF, the E's add up. We aren't really doing circuits, but if we were doing circuits, I would tell you that all the loops are in series. So all their voltages add up. And all that means is if instead of one loop, I have a nice little coil with a bunch of loops, and I have a bar magnet that we're moving or whatever to create an EMF, then the EMF will be minus n d phi b dt if you have n turns or n loops. So it just increases with the number. So if you're doing sort of an application or an applied problem, often they'll think about putting in a bunch of turns to increase the effect. If you're doing a theoretical physics problem, then you just put one, because all it is sticking an n right there. So geometry is important.